Okay, so we're still working on Unit 2 and vectors. Today we're going to be modeling real-world scenarios. So finally, why are vectors used? So first, our warm-up, I want you to find the dot products of the given vectors. So my first one, it gives me u and v. So u dot v will just be my 3 times 6 plus 9 times 5. All right, 3 times 6 is 18. 9 times 5 is 45. 18 plus 45 should be, C 50, 63, I believe. Hope I'm not wrong. That would be sad. All right. Now these two, it's giving me my vectors as a picture, okay? So if I have these two dot producted, okay, I'm still going to do x times x. So it'll be 8 times negative 7 plus my y's, okay? So it'll be 4 times negative 9. Okay, 8 times negative 7 is negative 56 plus 4 times negative 9 is negative 36. So that should be negative 92 as my dot product. Okay, last one, number 5. Okay, we've got 4 and negative 9 and 4. So I'll do my x's. 4 times negative 9 plus negative 9 times 4. So it should be negative 36 plus negative 36, which is negative 72. Okay. All right, carrying forward. There's a video that is also linked on the Google Classroom if you'd like to watch it for additional information about vectors. Okay. But really what we want to talk about briefly is orthogonal vectors. Okay, so we've mentioned this, that orthogonal vectors, look, a definition, write the definition down. All right, it's when two vectors form a right angle or perpendicular to each other, aka 90 degrees. Okay, what can you do to decide if two vectors are orthogonal? Okay, so we did work on this on the other day, where we figured out that vectors were orthogonal when we found the degree of direction of each and subtracted them and got either 90, negative 90, 270, or negative 270. But the faster way is the dot product equals 0. And that's going to be a lot faster because y'all know finding the dot product is significantly faster than finding direction. So, are the following orthogonal? We've got W and U, okay? So we're going to do 6 times 2, okay? We're going to do W dot U, which will be 6 times 2 plus negative 2 times 6. That's 12 plus negative 12, which is 0. Yes, they are. Yes, it's orthogonal. All right, and then let's do it again with these two. I don't feel like it's going to work out. Okay. So we're going to have negative 3 times 2 plus negative 2 times 1. So that will be negative 1 plus negative 2. That's negative 3. They are not orthogonal. Okay. So if your dot product is 0, the vector is orthogonal without us finding directions, okay? Can we write one that's orthogonal ourselves? Yes, we can. We just need to make something, we'll call it a W, equal to something, so that V dot W equals 0. So let's think about it. I'll have negative 7 times something plus 4 times something. Okay, I've got several options here. Okay, these are not the only two correct answers, trust me. Okay, what I like to do is I like to take my numbers I have and switch them, okay, and make sure that one of them is a negative times a positive, and the other one's a positive times a positive. So this will be negative 28 plus 28, which is 0. Okay, another option, so that would mean that my W could be 4, 7. So hopefully you can kind of see that pattern. Another one you could do, okay? Again, giving that same v. And I want v dot, we'll do u for this one, to equal 0. This one's the cheater way. Okay. So another one we can do, what if I multiplied by 0? What if I made u a 0 vector? Well, that's 0 plus 0, which is 0. So if I made u a 0 vector. Now these are not the only two that work. These are just the quickest ones I can find without having to think terribly hard. Okay? So make sure you've written down this fact, and probably this. Okay? Those will be helpful to you. All right, so we're going to apply vectors to the real world, and here I have some examples. So vectors can be used to model the movement of forces, such as wind, gravity, push, and pull. So if you had an object, okay, like this beautiful little box here, and the box is just sitting down, not moving, okay? The box is experiencing 3 forces at least. Okay, and we can model them all as vectors. The first one is gravity, and y'all are experiencing gravity right now. Gravity is the force that keeps us pinned to the earth. Okay, what's fun is what prevents us from being squished like pancakes is actually something called normal force, which as you can see is an equal opposite force to gravity, okay, which is preventing us from squishing like little marshmallows under a book. All right, and of course at all times there is friction that is preventing us from sliding around. Okay, but in our next picture, you can see if we have a force where the force is greater than friction, where will we go? Well, we'll have a motion vector. Okay, now as life gets more complicated, and if you study physics, there's rolling vectors. As you can see, our lovely swirl here. Okay, vectors do not necessarily have to form straight lines, but we are not going there. But there are other forces that are turning. Okay. Here's another example which you might realize makes more sense, okay? Let's think about the movement of a truck, okay? If the truck is moving forward, we'll say at 100 newtons of force, okay? What would this smaller force be? It could be wind resistance, okay? It could be friction from the road. Okay? There's a lot of things that could be slowing down this truck. It could also be going up a hill. Hills are spelled with H's, Miss Moore. All right. So there's a lot of things that are pushing back against the truck as it goes forward. So when we add those together, we actually know they're affecting each other, okay, and changing the amount of force that they actually experience in the real world. This is the kind of thing we're going to get a little bit more into, okay? So let's think about 2 examples of modeling vectors in the real world. So my favorite things to model, because it's easy to model, is wind, okay? I like to model wind because wind acts on its own and we don't have to worry about things like friction or hills, okay? So I'm supposed to model the force, for number 1, of the wind blowing due west at 11 miles per hour. And then it has a coordinate plane where I'm supposed to do this. Okay, due west. Could I imagine that my coordinate plane is really the cardinal directions, where north is at the top, south is at the bottom, west is on the left, and east is on the right? Yes, not only can I do that, I should. So in reality, this is north, this is south, this is west, and this is east. So I'm modeling my wind blowing at 11 miles per hour, okay? I'm going west. How much west am I going? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's 11. So could I make this vector? Yep, that's the vector I am looking for. Okay, so we are going due west at 11 miles per hour. So that's going to give it a magnitude, right? That magnitude equals 11. Okay, that's That's the length of the vector, and west is that way, to the left. All right, currents of rivers also work really well for this, okay? So current of this river, okay, so this is going to be my number 2, is flowing due south at 9 kilometers an hour, okay? So there's my magnitude here, and we're going south. South is down. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going down south at 9 kilometers an hour. So my vector will look just like that. Now do try to make sure you're ending at 9. If your art is not good, label it. That's all you have to do to apply vectors to the real world. Now, only problem is, do you think we're going to stay with just cardinal directions, where we go just left, right, up, and down? Okay, probably not. So, we will have some formulas. Do not panic. They're not scary formulas. All right, so here's our true real world. We're modeling the movement of a car driving 30 miles per hour at a bearing of north 20 degrees east. Okay, so there's a couple things we have to do. First thing I'm going to notice, 30 is my magnitude. That's how fast we're going. It's how much is the strength or length of the vector. So I'm going to represent it with an M from now on. The next part, and this is the trickiest part of these problems, is this. North 20 degrees east, okay? What that means, okay, when we have real world problems, is it's referring, compared to north, how far east we're going, which is that way. However, in math, when we want to do angles, angles are always formed here, okay, which is the opposite of what it gave us. So what you have to do is take 90 minus what it gave us, okay? So that would be 90 minus 20, so I am actually going at a 70 degree angle to the x-axis, okay? And 70 degrees is what I'm going to use in my formulas. Over here are my formulas. I have 2 of them. Why do I have 2 of them? Because I have an x value for my coordinate point, and I have a y value for my coordinate point. The x formula is m cosine theta, and the y value is m sine theta. What are we using as m? M will be 30. And this theta, which is a fancy symbol for a variable, okay, theta, you'll notice it's not a 0, it's a 0 with a wiggle, okay, just another variable. You can use z if it mattered, okay, will be 70 degrees, our 90 minus given, okay. So let me pull up Desmus real fast, I forgot to grab him. Desmus.com. That is not what I typed. Please forgive me. All right, scientific. Where can I put him? Still loading. Sometime soon. Alright, so for my x coordinate, I'm going to do 30 cosine 70. So I'm going to literally type 30 cosine 70. Okay, and so that's going to be 28.84. I know we're going to have to round on our coordinate plane. Oh, that's 704. That's wrong, isn't it? Oh, I'm so sorry, guys. So I'm going to get 10.26. I I'm so sorry for the incorrectness. I typed 704 instead of 70. Please don't make that mistake. All right, that's my x value. Okay. My y value will be almost the same formula, but instead of cosine, I will use 30 sine 70. Okay. And that one is 28.19. Okay, so that's my coordinate point. So what I'm going to do is look at my graph I want to graph this on and go, wait, I only have 10 available slashes. Do I have to make each one value of 1, or could I be creative and make them go by 2, 4, 6, 8? Yes, I could do that. Make it a little neater. Okay, I'm not going to label them 4, 6, 8, 10, except every 10. 12, 14, 16, 18, 20. Okay, and then going up, 10. Come on. Okay, I'm tortured. Now, looking at it, is 20 going to be enough? Nope. Okay, I need to fit nearly 30 on there. So, I'm going to go by 3s. So that's 3, 9. Oh my gosh, I'm tired. Please forgive me, guys. Three, 6, 9, 12, 15, 18, 21, 24, 27. That makes the end 30. I'm sure that's very legible. All right, so going by 3. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. So going 10.26. Now, will this be the most accurate thing in the world? Nope. There's my 10.26. Up 28.19. There's my vector modeling the car, and to make it very accurate, I can always do 10.26. Remember the old school version of math, if you're not got a good drawing, label it and it's correct. Alright, so that is the answer. Alright, your job is to do this 12 times, okay? Your first 4 are cardinal directions, so you don't have to use the formula, okay? Your first 4 are cardinal directions, so you don't have to use the formula. And the next 8, you do need to use the formula. You will have to modify some of them on your graphs because it will not be easy to do once. All right, you've done a great job. Ask me if you have any questions. Sorry that was so long.